Good morning. Today we have the lecture on higher order sliding mode control. The organization of today's lecture will be as follows. First, we have the introduction to higher order sliding mode control. Then we see the convergence of distance and time, so that the state trajectory convergence to the equilibrium point in finite time will be having a proof in this lecture. And then we implement the higher order sliding mode control on percutaneous interventions using bevel tip needle. In that research study, we implement the higher order sliding mode control and see the performance, how it is getting converged in finite time. And finally, we conclude today's lecture based on the sliding mode performance on the percutaneous interventions. Coming to the introduction, sliding mode control has several properties: finite time convergence, robustness, parameter variations, reduced order dynamics. The higher order sliding mode control retain most of these properties and is a generalization of the first order sliding mode control. Here in this higher order sliding mode control, higher order derivative is acted on the sliding variable sigma instead of influencing first order dynamics. That is, in the conventional sliding mode control we have seen z dot, that is sigma dot, is derived from the sigma variable, but here we go for sigma double dot, that is the higher derivative is involved in the dynamics of the sliding variable. Now, coming to the introduction, continued with the introduction. So, we have the sliding line is in such a way that we have two surfaces in perpendicular to each other, that is, one surface is, or one plane is sigma equal to 0 and sigma dot equal to 0 is another plane, and the intersection of these two planes will have a line, and that is the sliding surface, you can say, that is the sliding domain where the trajectory of the states should converge. That is the line of interest where the trajectory of the states must sit on it and get into the equilibrium point, that is sigma dot equal to sigma is equal to 0. And how this trajectory is getting converged to the equilibrium point is through multiple twistings of the state trajectory, and each time we see that the twistings distance as well as the time to reach the intersecting line is reduced, and that is the proof we are going to see, because we have taken from two planes, one is corresponding to sigma dot equal to 0 and another one is sigma is equal to 0. When these two planes intersect, we have a line of intersection, that is the line of interest, which is where the trajectory of the states will get reach there and slide it to the equilibrium point. So, now we see the proof for finite time convergence of the state trajectory. So, first we see distance proof, like distance convergence. That is, we have the state trajectory x1, x2, such that accordingly, so that this distance and this distance, when you compare, this distance is lesser than the starting distance, then this distance and this distance we compare, and then this distance is lesser than this distance. So that this proves that the trajectory of the state is getting converged to the equilibrium point in finite time. So, how much time is taken is the second proof we are going to see through time convergence. So, eventually what we prove through this higher order sliding mode controller is we have finite time convergence of the state variable to the equilibrium point, which was not possible through the conventional sliding mode controller. So, now we see the proof of distance convergence. So, we take here the quadrants x1, x2, this is the first quadrant, fourth quadrant, second quadrant, third quadrant. So, in the first quadrant, when you take the first quadrant with the state model x1 dot equal to x2 and x2 dot is equal to u, where the control law is coming in the state equation, which is equation 1, and x2 dot is equation 2. Then we have the control law for this higher order sliding mode controller is taken to be minus k1 signum of x1 minus k2 signum of x2, which is equation 3. So, in the first quadrant both x1 and x2 are positive. So, from 1 we have x1 dot equal to positive and x2 dot is also positive. So, x1 dot positive implies this is the direction of x1 dot, and x2 dot here, if you see, I just made a mistake, sorry, that if you see that this is basically x2 dot turns out to be negative, because when we substitute x1 and x2 positive in the u equation, equation 3, what we have is minus k1 into positive, that is 1, minus k2 into plus 1. So, eventually it is negative, since k1 is greater than k2, which is positive values, is a constant non-zero values. So, we have x1 dot trajectory being this one and x2 dot trajectory is negative. Thus, the resultant is this direction. So, in the first quadrant what we have is x1 dot x2 dot. So, we have the direction of the state trajectory is in this way. Similarly, in second quadrant what we have is x1, sorry, we can take the fourth quadrant because we come in this direction. We take first quadrant 1 and then quadrant 4. So, in the quadrant 4 what we have is x1 is positive and x2 is negative, which leads to the resultant in such a way that x1 dot equal to x2 and x2 dot equal to u, which is a state variable. When you substitute here, what we obtained is x 1 dot is negative and x 2 dot is given by negative. So, we have both coming out to be, that is x 1 dot direction is this one and x 2 dot direction is down. So, the resultant is this one, that is the direction of the state variable is this one. So, I put here this is x 1 dot and this is x 2 dot. So, the resultant is this one. Next we go to the third quadrant. What we have is both x 1 and x 2 are negative. So, from equations 1, 2, 3, which is x 1 dot equal to x 2 and x 2 dot equal to u and u equal to minus k 1 signum of x 1 minus k 2 signum of x 2, we have the direction, that is x 1 dot equal to negative, similarly x 2 dot is equal to positive. So, we have this direction x 2 dot being positive and x 1 dot being negative. So, the resultant is in this, that is the state trajectory's direction is in this way. And similarly, in the fourth quadrant we have the direction of x 1 dot is in this way positive and x 2 dot in the second quadrant. It is not fourth quadrant, it is in the second quadrant. We have both x 1 dot and x 2 dot are positive. So, the resultant is this one, that is the resultant, which is the state trajectory's direction. Therefore, we have the trajectory of the state variable coming out to be this direction, then this direction, then this direction, then finally this direction, which shows that it comes this way and goes this way, then goes this way and goes this way. So, we need to prove that this trajectories of the state variables will converge to the equilibrium point in finite time. So, the distance must be now observed, whether it is each time getting reduced. So, what we do here is we take the situation in such a way that s equal to x 1 and s dot equal to x 2. So, s double dot is equal to u, which implies minus k 1 signum of x 1, which is s in this case, minus k 2 signum of s dot. So, s double dot is in general given by ds dot by dt, which is equal to ds dot by ds into s dot, which is equal to minus k 1 signum of s minus k 2, which is u signum of s dot. So, in the first quadrant, what we prove is we have, because s equal to x 1 and s dot equal to x 2, we have dx 2 by dx 1 into x 2 is equal to minus k 1 signum of x 1 minus k 2 signum of x 2, which can be written like this: x2 dx2 is equal to minus of k1 plus k2 into dx1, depending on the sign of x1 and x2 in the first quadrant. Both are going to be positive and hence signum will give plus 1 values for that. So, integrating both sides we get x2 0 to 0 x2 into dx2, which is equal to integration of 0 to x1 of minus k1 plus k2 into dx1, which leads to x2 naught square by 2. This is basically minus part is here, which is equal to minus k1 plus k2 into x1. Thus, in the first quadrant we have x2 naught square is equal to 2 into k1 plus k2 into x1, which is schematically it is given by x1, this is x2. So, here it is 1. So, here we start from x2 naught and this is a O value and say this is P. So, in the first quadrant this is the situation. In the fourth quadrant, which is going to happen like this, which is say this is P1 and this point is P2 and this is origin. So, it is O. So, for the first quadrant the left hand side as the limits from x2 0 to x naught, whereas the right hand one has the limits varying from 0 to x1. So, now what we have observed is x2 naught square equal to 2 times of k1 plus k2 into x1. Similarly, in the second quadrant we have, in the similar procedure we have x21 square equal to 2 times of k1 minus k2 into x1. So, basically it is not second quadrant, it is basically this quadrant, which is basically the fourth quadrant. I am just making the mistake, sorry. So, this is basically the fourth quadrant, we have this relationship because k1 greater than k2 greater than 0. So, the distance ratio OP2 by OP1, OP2 by OP1, we have x21 by x20, which is equal to root of k1 minus k2 divided by k1 plus k2, which is equal to a variable q, is a constant which is less than 1. Therefore, we generalize. So, we generalize x2 of I plus 1 by x2I is equal to q, which is less than 1. So, here between x2 0 and x2 1 we have the relation x2 1 equal to q into x2 0. Since q equal less than 1, since q less than 1, x2 1 is less than x2 0. So, this guy x2 1 is less than x2 0. So, we prove that, we are proving that this distance, that is the distance travelled from this to this by the state trajectory, is greater than the distance travelled from this point to this point P2 from the x1 axis is greater. So, the distance OP2 is lesser than distance OP1, that is proved here. Likewise, we can prove that accordingly from each quadrant to quadrant. Now, coming to the time convergence, we have proved now in the state trajectory the distance is converged, whereas the time convergence is another parameter to be proved in order to reinforce this statement that it is converging in the finite time. So, now coming to the first quadrant, what we have is from x 2 0 to 0 dx2 is equal to minus 0 to t naught k1 plus k2 into dt. What we have after integration is x 2 0 equal to k1 plus k2 into t naught, which implies your t naught is x 2 0 by k1 plus k2, say it is equation 1. In quadrant 4, we have the limits varying from 0 to minus x 2 1 dx2, which is equal to minus of integration 0 to t1 of k1 minus k2 because of the signs of the variables x1 and x2. We have this one, which further giving the value of t1, which is equal to x21 by k1 minus k2, say which is equation 2. Or we can take t1 is equal to mod of x21 by k1 minus k2, because whatever being x21 negative or positive, it will give the positive value only, that is why we have taken the absolute value. Now, the total time t1, say t naught plus t1, which is given by x2 naught by k1 plus k2 plus x21 by k1 minus k2, where we take x2 naught outside. Why? Since x2 naught 21 is equal to q times x20, we have proved that x20. So, we can take x2 naught common, so q by k1 minus k2 plus 1 by k1 plus k2, which implies t1 is equal to some constant, because this full variable, this full part is a constant. So, eta into x2 naught. Similarly, t2 is equal to eta into x21, which implies t2 is equal to eta q x2 naught, which can be generalized in this way, that t I plus 1 is equal to eta q I norm of x20, which implies t I plus 1 is equal to eta mod x2 naught by 1 minus q, which implies convergence of time. Thus, we have proved that both convergence of distance as well as convergence of time for the state variable trajectory in this higher order sliding mode, which proves finite time convergence. So, now we come to the implementation of this higher order sliding mode control strategy on the research study, on our research study on percutaneous cancerous interventions using bevel tip needle. So, what is a bevel tip needle? So, this is the bevel tip needle, where the tip is having this shape, bevel shape. The bevel angle is given by this one, which can vary from say 45 degrees to 75 degrees. So that once the tissue reaction is happening here, once it is this needle is inserted into the tissue domain, the tissue reaction force happens on the bevel surface, on the surface of the needle tip. So, the needle will undergo this type of bending because of the tissue reaction force on the bevel surface. Then the needle can be spinned along the needle axis in order to have the direction change, either upper direction or lower direction, depending on the spinning of this needling surface, or around the needle axis the needle must be rotated in order to have the direction of curvature. So, here we have two inputs, one is the insertion input, another one is the rotation input for the needling system. So, the objective of this research study is to keep this needling system in the plane of interest, desired plane of interest. So, this is the plane of interest. Once a needle is inserted in the tissue region, the needle must be lying in the desired plane of interest. It must not be diverted away from the plane of interest. So, that is the objective. So, must the desired objective is the needle must lie in the desired plane of interest while maneuvering inside the tissue region. This is the important objective of this research study, and we have taken or considered the system states, the needling system states, in order to satisfy the objective, or the system states, or the distance away from the plane that is shown in the figure. The blue plane is the plane of interest, and the distance away from the plane is first state, which must be controlled so that the distance should be minimized or made it to be 0. Finally, the state variable must lie on the plane, which implies this state variable S1 equal to y must be 0. Another state variable, second state variable is the first state variable, the second state variable is the rotation around the z axis, which is say alpha, must be minimized. If it is rotated around this axis, then the out of the plane of the needle happens. So, the angle around the z axis alpha must be minimized, that is the second state variable must be converged to 0, this variable. Similarly, the third state variable which must be converged to 0 in the finite time is the rotation around x axis, which is gamma. So, the three state variables are distance away from the plane of interest and rotations around z axis alpha and the rotation around x axis gamma. These are the three state variables that must be converged to 0 in the finite time. So, the results we have obtained in implementing the higher order sliding mode control strategy are as follows. First, we have implemented conventional sliding mode strategy on our system model, kinematic model, based on the bicycle modeling of the passive needle, which is with the bevel tip of 45 degrees bevel angle. So, the state, first state is getting converged, and the second states, that is the angle. The first is the distance state shown separately, and the angle states S1 and S2 are shown here, where we notate them by R1, R2 and R3, and the controller is having the chattering high frequency control input, which is this chattering effect that can be shown, and we see that the sliding variable is getting converged in finite time. That is what you have seen here with the conventional sliding mode strategy. So, here we see the conventional sliding mode strategy without the presence of disturbance. So, this can be the same system performance, the evolution of the states and the control input without chattering can be observed by a simple state feedback controller u equal to minus kx can also be used to observe this, because there is no disturbance in this control problem. So, when we give disturbance, what happens with the conventional sliding mode control strategy? The control input is feasible without any chattering. The states, you see the convergence is suffering, the distance state is not getting converged. Likewise, when we zoom this, we have the other states, angle states are also not converging. So, when the disturbance is given with the conventional sliding mode controller strategy, we have the evolution of the states and control input in such a way that the states are not getting converged at all in finite time. So, we go for the strategy called integral sliding mode control strategy. So, the integral control mode sliding strategy is with the nominal control plus discontinuous control. When we have the discontinuous control with the integral sliding mode control strategy, we have the high frequency components existing in the control input. So, even though the states are converged in finite time convergence is observed with the integral sliding mode strategy, but the controller is having a chattering problem because of the high frequency component here, which is not feasibly acceptable in the clinical scenario of percutaneous needling interventions. So, the discontinuous part in the integral sliding mode controller, this is nominal control plus super twisting controller is used. Instead of the discontinuous part of the integral sliding mode control, we have used the super twisting mode control, where this controller replacing the discontinuous part in the integral sliding mode control gives finite time convergence of state variables and chattering free control input, which is desirable in the clinical scenario. And the experimentation is shown here. With this strategy implemented on the real system, we have observed that the needling system can be inserted with the bevel tip, so that the angle diversion from the plane, that is the line of insertion, is shown here. So, that this video confirms that due to integral sliding mode control with super twisting algorithm, the needle lies within the desired plane of interest with the bevel angle coming into picture because of the tissue reaction force. Thus, we conclude that higher order sliding mode control confirms finite time convergence of the system states, and we have also, by this lecture, we proved that both time convergence and the distance convergence, in order to reinforce the statement given for the higher order sliding mode control in terms of convergence, and we have performed this robust control strategy on the percutaneous needling system for cancerous treatment, and we observed that the integral sliding mode controller with the discontinuous part being replaced by the super twisting control strategy gives a very better performance when compared to the other strategies. With this we wind up. Thank you so much.